It is my pleasure to introduce our next speaker, Dr. Hwaseong, who is the Corporate President and CTO of Samsung Electronics Device Solutions business, leading the Semiconductor R&D Center. Prior to his appointment as the President and CTO, Dr. Song served as EVP and head of the Semiconductor R&D Center, responsible for managing a broad range of semiconductor R&D activities from fundamental research to chip-level testing and driving innovation in DRAM, NAND Flash, advanced logic and package, as well as new memory and sys device technology development. Dr. Song started his career as a DRAM process engineer at Samsung in 1996 and has held several management positions in flash memory product and technology development at Samsung's memory business. Before joining the R&D Center, he has been mainly responsible for driving the company's NAND Flash memory technology development, starting with the planar 2D structure in 2004 and the revolutionary vertical 3D structure in 2013, which has become an industry standard since its groundbreaking introduction. He has played a key role in pioneering VNAND technology solutions for 7 consecutive generations. In 2017, he was presented with the Korea Technology Award and Presidential Award by the Ministry of Trade, Industry, and Energy for the development of the 64-layer 4th-generation VNAND solution. Dr. Song holds a doctoral and master's degrees in electrical engineering from Seoul National University and a bachelor's degree in electrical engineering from KAIST. Please welcome Dr. Song.
Thank you so much, Tom. Good morning, everyone. As you introduced right now, I'm Hwaseong, CTO of Samsung Electronics Device Solutions. First of all, thank you for inviting me to this remarkable event. It is a great honor to meet all of you, pivotal players in this special semiconductor industry. Today, I'd like to discuss the future of AI and memory technology under the theme, AI Revolution driven by memory technology innovation. As you may have already observed, AI has become an essential part of our daily lives. Recent advancements in semiconductor technology, coupled with the exponential growth in data, have ignited a third wave of AI development. As you can see, a left plot, AI is evolving at a pace that surpasses any other technology that has defined the previous era. As a platform, AI is poised to transform and advance technologies across countless fields: bio, transportation, robotics, manufacturing, finance, security, and ultimately enrich our lives in ways we can only begin to imagine. That's why I believe AI is a technology with immense potential for sustainable growth, and we are truly, I think, at the forefront of this transformative era. Semiconductors, as you know already very well, play a critical role in AI with their development centered around replicating the functions of the human brain, I think. First, the human brain perceives information, much like how image sensor operates in semiconductors. Next, the brain processes the sensed information, much like how a CPU, GPU, or NPU functions as a processing unit. Memory can be thought of as the system that stores and retrieves the processed information. Now, let's draw an interesting comparison between the evolution of the human brain and the history of AI. The human brain has evolved over approximately 3.4 billion years, evolving from single-celled organism to its present-day complexity. Given the limited resources on Earth, humans typically consume around 2,500 kilocalories a day, with about 20% of that energy being used by the brain, despite it accounting for only around 2% of the body's total weight. Therefore, the human brain has evolved to maximize efficiency. making the most of limited resources with minimizing energy consumption. On the other hand, in just 80 years, AI has made incredible strides, reaching levels of accuracy far beyond what was initially possible. Since the Turing test was introduced in 1950, the focus has been on increasing computing power to improve reliability and accuracy. In the past 5 years, we have seen computing power increase by nearly 1 million times. And as you can see on this plot, one of the key metrics for AI accuracy, the MMLU score, has jumped from 32% to 92% in just 5 years. Despite this remarkable progress of AI technology is still a long way from fully matching the capabilities of the human brain. While we have seen AI models that surpass humans in terms of accuracy, the human brain still has a clear edge when it comes to the data processing speed, energy consumption, and storage capacity. I'm sure many of you already share my thoughts on this. Lately, I have been reflecting on the work still needed in the semiconductor industry to close these gaps. What excites me is that the company I'm a part of, Samsung Electronics, has the potential to make a real impact in addressing these challenges across every area: memory, foundry, and absolutely packaging. To realize the potential growth of AI, there are still many challenges to overcome across different fields. Today, I'd like to focus on issues related with memory technology. In the AI era, there are 3 key challenges that need to be addressed: the rapid increase in power consumption in the AI era, the performance limitations of AI due to memory bandwidth constraints, and the issue of insufficient storage capacity. First, let's talk about the power consumption required for AI training, very famous one. With the emergence and the advancement of generative AI, the number of model parameters has increased dramatically, leading to a significant rise in power consumption for training. Training ChatGPT-4, which has around 1.8 trillion parameters, requires around 148 gigawatt hours. This amount of energy is nearly equivalent to fully charging 2.5 million Tesla Model Y vehicles, and it is also comparable to the total number of cars exported by South Korea in 2023, which was around 2.7 billion, huge energy. The second challenge is the memory war. With the advancement of generative AI models, GPUs have seen their computational power increase several-fold with each generation. However, memory bandwidth has only increased by a few dozen % with each generation, creating a growing disparity between the increase in computing performance and the available memory bandwidth. The third challenge is insufficient storage capacity. To address this critical issue of hallucinations in generative AI technology and to improve reliability, retrieval augmented generation technology was developed. This technology requires vector databases that are several times larger than the original data, and it needs high performance and high capacity SSDs. To address these issues, we should not only focus on the continuous advancement of high performance and low power products, but also develop solutions specialized for on-device AI. And we should also pursue innovative memory architectures as well. Achieving these goals, I think, is only possible through collaboration among valuable partners like you here. In the second chapter, I will introduce memory technology and product strategies for addressing the key challenges in the AI era that we discussed earlier. First, I will introduce our high performance and low power products. The development speed of HBM is so impressive. You can see from this table that new HBMs are being developed every 2 years. This year and next year, maybe HBM3E is the star. And one HBM3E provides a bandwidth of over 1 terabyte per second through 1K IOs and high-speed signaling of more than 8 gigabps. In the upcoming HBM4, the number of IOs will double to 2K, and the DRAM die will be stacked 16 layers higher to provide even greater capacity. Another important change is that the logic process, rather than the existing DRAM process, will be used for the base die. Performance and power improvements will be significant, but I think it's also meaningful in terms of customization. HBM achieves high energy efficiency among DRAMs by using a 2.5D structure with a silicon interposer to shorten the length of the channel less than 6 millimeters. However, various methods are being researched to achieve even higher capacity and efficiency while maintaining the high bandwidth of HBM, one of which is absolutely custom HBM. As mentioned earlier, in HBM4, the use of logic processor on the base die allows for the production of custom HBM that meets customer requirements by applying the concept of foundry business. The channel length can be reduced to around 2 millimeters using the die-to-die interface, or under 1 millimeter by integrating logic into a base die by utilizing stacked DRAM and TSV interface to reduce power. Also, using a die-to-die interface in custom HBM reduced the required number of IOs and IO pie area, enabling more IP into a base die. To scale up the storage capacity in a limited form factor, we face challenges in various technical perspectives. First, we need high integration of bits on a cell, more dies on a package, and mounting space optimization to have more packages on PCB. Second, the increased data capacity due to high integration raises the burden of ensuring data reliability. So, we need advanced data recovery mechanism to ensure data reliability for high-capacity SSDs. Third, cooling technology are also essential to utilize full performance of SSDs. As multiple NAND chips are connected to a channel to build ultra-high capacity SSDs, signal degradation can occur due to stub effects. DQ swapping changes the packagable map in a way that removes the stub effect. In addition, signal integrity margin and crosstalk issues becomes more serious as the NAND I/O frequency is increased. To address this issue, advanced equalizers along with training, retraining technologies, and DQ shielding technologies will become essential ones. With the introduction of PAM4 signaling in PCI Gen 6, SI margin is significantly decreased compared to the non-return to zero signaling of PCI Gen 5. The design complexity of high-capacity SSDs makes them easily affected by power noise sources. Power noise from various active ICs and PMICs can induce additional jitter, known as power supply-induced jitter. This PSIJ is transmitted through the hierarchical power distribution network. The PCIe SI margin reduction exacerbates the jitter problem as well. So, PDN optimization is also a critical part in designing ultra-high capacity SSDs. The primary advantage of SSD solutions absolutely lies in their capacity and performance. However, Security and availability are also critical for AI systems. So self-encrypting SSDs provide data security with strong key protection, and SSDs ensure firmware integrity by using hardware-based root of trust. Using reliability technologies, we ensure SSD continuous operation even if some NAND dies fail. It is also important to predict SSD failures. So we are working closely with customers to facilitate telemetry-based failure prediction in large-scale data centers. Next one is CXL technology. CXL is definitely beneficial to both end customers and the industry. The first CXL memory expander was introduced in 2022 and has been working closely with the industry since then. As a result, many different types of product lines based on the usages and applications have been introduced. CMMD stands for CXL Memory Module DRAM, which is suitable for memory expansion, and CMMH is a hybrid with flash memory, which has two types, tiered and persistent, which are more suitable for cost-effective solutions, but require much larger capacity. All of these can be pooled in a rack scale so that memory can be accessed remotely and shared across multiple servers through the network. So CMMB was successfully demonstrated as a reference system. CXL technology offers XPU-agnostic compatibility, enabling seamless integration of CXL memory modules with any comparable system. Furthermore, CXL is memory agnostic as well, so it supports memory sharing across systems and does not depend on specific DRAM or NAND generation, provided performance and capacity requirements are met. All this means better TCO for end customer with flexibility. By the way, CXL solution is not just for TCO in mind, but as you know very well, performance benefit as well. For memory-intensive workloads such as DLRM, database, it can improve overall performance. For instance, CMMD reduces DLRM training time by around 10%, and for graph database, execution time is reduced up to 50%. Since CXL technology allows memory expansion beyond the CPU's memory channels, I think there are just a few examples, and the potential of CXL technology is beyond our imagination. Another approach to addressing key challenges in AI era is to maximize the use of on-device AI solutions implemented in various edge devices, such as mobile phones and PCs. That way, we can reduce the burden of relying solely on the cloud for AI implementation. With that in mind, now, I'd like to introduce our on-device AI solutions. We understand the importance of power at the edge and on-device. Unfortunately, there is no ultimate solution that can deliver both power efficiency and performance in traditional way. On-device AI applications require much higher bandwidth than existing LPDDR while maintaining power efficiency. To achieve this, we reduced the I/O speed, increased the number of I/Os, and designed a new compact and balanced pad to compensate for these increased numbers of I/Os. This allows LPDDR Wide-IO to deliver around 166% faster speeds while reducing overall power by 54% compared to LPDDR5X. And additional power reduction with vertical wire bonding will be available for very near future. Memory industry is working closely with the SoC manufacturers and working on JEDEC standardization. The first mobile products with LPW are expected to be released by 2028, which will be a significant advancement in mobile AI. PIM, processing in memory technology, can be applied to various types of memory. And while the instructions of conventional DRAM are input into a specific bank, the instructions of PIM operate in parallel across all banks. And this data is supplied to the ALU FPU near the bank. By performing bank operations in a parallel manner and reading out the computed values in the end, high efficiency can be achieved in data processing with low reuse, such as metric vector math. Through these PIM concepts, two main objectives can be achieved in AI systems. First, it can expand memory bandwidth. PIM technology significantly improves effective bandwidth by executing instructions close to memory banks, which can improve performance by offloading simple memory-bounded calculation. Second, energy efficiency can be improved. Since input-output consumes more energy than DRAM cell accesses, performing computations directly within DRAM can reduce the energy consumption significantly. Therefore, PIM technology is attracting attention as a promising technology for overcoming the memory limitations of AI systems. Let me introduce you the LPDDR5X PIM that is being developed by applying PIM technology to LPDDR5X. The first reason for targeting LPDDR as the target of PIM technology is that the customer's goal of using LPDDR, performance and energy efficiency, is the same as what PIM aims for. Compared to DDR5, LPDDR5X has 1.5 times higher bandwidth per pin and uses more than 60% less than energy when transmitting the same capacity. These features reinforce the basic concept of PIM, enabling us to provide customers with more efficient systems. Secondly, LPDDR PIM can maximize the benefits of the rapidly growing on-device AI market. In terms of cost, privacy protection, and low latency, on-device AI technology has advantages, and PIM can provide an energy-efficient and high-performance solution at a lower cost than existing memory solutions. The application of this PIM technology shows notable performance gain in on-device LLM inference. In the Samsung Galaxy S24 Ultra system, simulations with Meta Llama 3 8B model revealed a 6-fold improvement in GMV layers and a 3.09 times boost in the decode stage. Finally, I will introduce a few innovative memory architectures that transcend the trade-off relationship. On this page, let me briefly introduce the next generation of device technologies that will enable continuous DRAM scaling. The structure on the far left represents the current 6F scale cell structure of DRAM. To fundamentally increase capacity, a 4F scale cell structure is required. Memory industry is currently developing a minimum-sized vertical channel transistor with a cell capacitor directly above the cell transistor. Another technology that can dramatically increase capacity is stacking cells vertically, similar to VNAND. Unlike VNAND, DRAM requires separate capacitors, making it challenging to implement stacking technology. However, recently, solutions are being developed and progress is being made. Additionally, memory industry is also developing the cell-on-pair structure, which transcends the current 2D architecture. Through these new technologies, next-generation DRAM with high bandwidth and high capacity meeting the needs of our customers will be realized. In the mid-long term, we plan to introduce a new HBM architecture optimized for AI computing environments to provide the best solution. As AI models continue to grow, the demand for memory bandwidth and capacity is increasing with rising power consumption issues. Current architectures struggle to address these demands and issues effectively. Breaking down the power consumption of HBM, it was revealed that the power consumption occurs during data transfer between HBM and GPU. Memory industry is looking into introducing an innovative structure that minimizes data transaction between HBM and GPU by locating accelerators within the base die and connecting these accelerators directly to the core die by TSV process. VNAND successfully started mass production in 2013, opening a new chapter in the memory industry. Nowadays, bonding VNAND technology allows for further scaling down of the periphery, enabling the achievement of high performance of 4.8 gigabps, and is already being rapidly adopted across the industry. Memory industry leverages the strengths of bonding VNAND to not only implement bonding between periphery and cell, but also extend this technology bonding between cells themselves. And this will enable us to stack more than 1,000 layers, pioneering this industry once again with multi-bonding technology. Memory industry is also dedicated to advanced packaging technology. To enable the stacking of HBM beyond 16 layers, next generation bonding technology called as hybrid kappa bonding should be developed. Hybrid kappa bonding technology offers approximately 30% higher stacking and 20% lower thermal resistance compared to conventional TCB. At the system level, memory industry is developing super large 2.x package technology capable of mounting more than 12 HBM units. It is going to be implemented using RDL technology and silicon bridge as well. What's more, memory industry plans to apply this hybrid kappa bonding technology even to 3D integration to get higher bandwidth, lower power, and higher capacity. Furthermore, memory industry recently is also preparing an iCube solution for high-level integration beyond Moore's law. The iCube-S technology, which uses a silicon interposer to create a 2.5D structure, is already in mass production. And the iCube-E, iCube-R technologies, which utilize a panel-level RDL interposer, are soon ready to provide a turnkey solution capable of heterogeneous integration, including processors and memory. By doing this, even 16 HBMs will be integrated in a package. Various memory segments have trade-offs in cost and performance. Compared to conventional memory hierarchy, modern memory systems have a deeper one. As applications need more capacity and higher performance, new memory segments are introduced to meet those demands. Supporting the new memory hierarchy requires rethinking system software architecture. Memory and storage vendors must also provide software solutions to maximize hardware potential. To this end, memory industry is actively collaborating with the open source community, operating system vendors, and standardization organizations, such as Open Compute Project and SNIA, to build an ecosystem for the new memory storage hierarchy. These efforts are aimed at maximizing the benefits of memory and storage solutions across different AI systems. As you can see on this plot, Memory industry is preparing an extensive product portfolio with innovative technologies to offer optimized solutions across all applications centering around AI. Samsung Electronics has memory solutions that can cover nearly everything from the cloud to edge mobile. So, what can get us to quantum jump of memory and AI? Over the past 70 to 80 years, we have faced numerous challenges while envisioning the AI era, and we have recently achieved remarkable advancements. To further accelerate this progress, it is essential to integrate collaborative approach, not only from companies such as memory, foundry, material, equipment providers, and EDA companies, but also from institutes, research institutes, and notable academic circles involved in R&D process. This close cooperation, I think, will foster innovation and growth throughout the industry, continuously driving progress toward our shared goal of creating a better future. It is my sincere hope that today's gathering will serve as a foundation for everyone here to advance into a brighter future of AI and memory technology innovation. Currently, AI falls short in terms of both efficiency and capacity when compared to the human brain. However, in the near future, I believe advancements in memory technology is expected to play a critical role in bridging this gap. Thank you very much for your attention.